So should I start?
Sure, ma'am.
Okay.
We can
So let
start
me
and
share. Yeah, thank you. Let me share my screen and then I will continue. So is it visible at PPT mode? Slide number 21.
Yes, ma'am.
Right, right. So good morning to all of you. We are discussing uh, uh, we have already started introduction and the classification. Basically introduction we have already done for CED2 course. So in the last class basically we have focused on different type of heat exchangers which are primarily used in chemical industry, and their functioning briefly, and in what which case what should be, what which one should be used. Okay, that we have discussed. And then we have started with basic design parameters, where the basic equation you people are already aware: Q is equal to UA delta T, basic equation of heat transfer. Another equation is MCP dt. Okay, so uh, these two equations only we will use to design the heat exchanger, or we can say heat transfer equipment, right? So in that equation, Q is equal to UA delta T, mean how each parameter will be counted in designing. That we are discussing how U will be counted. And U, if you consider, this is the combination of five different terms. Okay, so each term will depend on some geometrical parameters which depends on the area. Okay, so we have already discussed in the last class that this design of equipment, heat transfer equipment, is usually iterative approach, where we need to assume a certain value of overall coefficient, and then we further proceed to calculate overall coefficient, and then we will compare with the assumed value, right? So that we have discussed. And further, in overall coefficient there is a term dirt coefficient. So the dirt coefficient we have also discussed, and this is a table which is given in volume 6, and this table you can use as a guideline to choose the fouling factor. Now for any fluid, let's say if you are considering cooling water, there is a range. So how you need to fix the value? Okay, any value in this range you can choose, but the better approach is to choose the average one. Okay, in the range. So that you need to consider. So this is about dirt factor and overall coefficient. Next parameter we have in basic design equation is the mean term, mean temperature term, and that is basically delta T mean. Okay, mean temperature difference we call it. And if you consider a double pipe heat exchanger or shell and tube type, okay, we basically consider over here uh, the basic mean temperature difference, and then we will consider the variation which is possible because of shell and tube, because of movement of fluid in shell and tube heat exchanger, right? So here we will discuss based on double pipe heat exchanger, and the uh, mean temperature difference which we define over here is your LMTD, log mean temperature difference. Okay, why LMTD? Because that you know already, because from inlet to outlet continuously temperature varies, and that variation is in most of the cases that variation is not linear, that is non-linear. Okay, some variation uh, we obtain in non-linear nature, and to counter that we consider log mean temperature difference, not arithmetic mean. Okay, and that you already you must have already read in heat transfer course. So we are not going into detail that how this derivation, how this LMTD will be obtained and all. We consider that that LMTD equation, LMTD formula you already know how to derive. We will start from there. Okay. Now, if you consider double pipe heat exchanger, as far as flow are concerned, there are two possibility. One is the counter current flow, another is the one is co-current, another is counter current. Okay, in two ways only the flow is possible in double pipe. I'm not talking about shell and tube, that is in double pipe. Okay, so if I consider counter current flow of fluids, then how we can consider LMTD? This equation you people have already read. Okay, so if you consider this is a delta T mean, and M is basically LM, log mean, right? So that is T1, capital T1 and capital T2 are inlet and outlet temperature of hot fluid. Similarly, small T1, small T2 are inlet and outlet temperature of cold fluids. Okay, so this is the LMTD for counter current. Okay, you can also derive the uh, LMTD for co-current. Okay, in that case, the terminal differences will be capital T1 minus small t1 and capital T2 minus small t2. As you can see, this is different over here. Okay, so counter current LMTD you can calculate, there is no issue. However, when we consider shell and tube heat exchanger, okay, yesterday we have discussed the shell and tube heat exchanger, and if you see its geometry, we have number of tubes, right? Number of tubes, and the fluid, one fluid flows in the tube. And if I'm having, let's say, if I'm having a double pass in shell, in tube side, okay, I hope you understand all this. Double pipe, sorry, double pipe nahi, that should be double pass. Okay, one pass in shell and two pass in tube, so that we call as 1-2 shell and tube heat exchanger. So all if I consider two passes, all number of tubes will be divided in two. Okay, so in one, fluid will move in let's say from left to right. Okay, other set of tubes, fluid will move from right to left. Okay, further, if I consider this along with fluid which is moving in shell side, okay, please try and to understand that in tube side fluid is moving twice, right? From left to right and then from right to left. Okay, further, if I consider fluid in shell side fluid will enter from one nozzle and it will cross some of the tubes, because a baffle is there, so fluid of the shell will not directly move in from left to right or right to left, but it will move from top to bottom first. Okay, so it will cross all the tubes, right? And then it will change its in direction, and it will come in the, that we can say, the horizontal movement, and then again the vertical movement will be there, because we are considering sinusoidal movement in shell. Okay, so if you consider shell and tube heat exchanger, we come across all uh, we come across different type of movements. There is co-current, there is counter current, and there is cross flow. Okay, so mix kind of flow we usually observe in shell and tube heat exchanger. Okay, so that could be different than whatever we have considered in double pipe. Okay, double pipe may have either co or either co or counter, not the mixture. So in that case, what we can consider to because all these movement give different LMTD or different mean temperature in comparison to log mean temperature difference, which we have defined for double pipe, considering co-current and counter current. Therefore, for delta T mean in shell and tube heat exchanger, we consider LMTD, which is usually defined for counter flow. Okay, please keep in mind here it is not for co-current. We considered this for counter flow, and then correction we have considered, that is FT correction factor. Okay, FT correction factor also you have read in heat transfer course, to counter the multiple flow in a single unit, okay, or single exchanger. Okay, so delta T mean is true temperature difference, FT is LMTD correction factor. So FT, if you count, maximum value of FT could be your 1 value. Okay, so LMTD mean should be, maximum value should be equal to LMTD only for counter flow. Okay, please consider this is counter flow. So FT value should be equal to 1 only. However, when we consider FT correction factor, it depends on other parameters also. So let's see that what these parameters are. So FT correction factor, when we consider, we usually define two different parameters. Based on that, this FT will be counted. One parameter is thermal effectiveness of exchanger. Thermal effectiveness, that is capital P, and second is the ratio of heat capacity flow rates. Okay, so if you consider this P, in some of the books it is also shown by S, okay, capital S. So this P is whatever we are considering, this P is the uh, thermal effectiveness of exchanger. How it is defined, if you see this THI minus THO, that is hot fluid inlet and outlet temperature, and this THI minus TCI, this is basically inlet of hot and inlet of cold. Okay, what is the meaning of this? If you consider this particular parameter, this is maximum possible temperature difference available in a heat exchanger, right? Because nothing can be more than THI and nothing could be less than TCI. I hope you understand my point. So this THI minus TCI, that is the maximum possible temperature difference, and this is the temperature difference of one fluid. Okay, there is no point like here you cannot consider for colder side, you can consider TCO minus TCI also. Okay, but if I consider this P, the maximum value of this P factor should be 1 only, because nothing is more than that. Okay, if anyhow this is not possible that this difference will be equal to this, but if it is equal, that could be the maximum possible condition. Okay, so this P value should not be more than 1, right? Further, if I consider this capital R, that is heat capacity flow rate, so this is CPH minus CPC. This is not a specific heat, this is heat capacity flow rate, means this is MCP. Okay, this capital C is basically MCP of hot fluid divided by MCP of cold fluid, right? So heat capacity flow rates, and if because MCP over here, so we will remain with temperature difference only. So here I am having TCI minus, sorry, TCO minus TCI divided by THI minus THO. Okay, so as I was telling you that in this P you can consider this THI minus THO as TCO minus TCI, right? If you are considering here temperature difference of cold fluid, then this R should be CPC minus CPH. It means whatever is available in this denominator, that should be in numerator in P. That is the combination of this P and R. Okay, don't get confused. Like here, if you are using, you cannot reverse this. Okay, so whatever is available in numerator in P, the same value, same term will be available in denominator of R. Okay, I hope you are getting my point. So in that case, P and R you can calculate, and you can find this graph you must have seen in your heat transfer course also. So on the y-axis I am having ft value, and on x-axis I am having p value, which is maximum value of over here is 1, and I am having different curves representing r. Okay, now this is for one shell and two pass only. Okay, so if you consider two shell and four passes, okay, this is 1 2 2 4 3 6, like that it move. So for all these combination, ft correction factor graph would be different. This is only for 1 2, for 2 4 graph will be different, right? Same pattern, but values will be different over there. Okay, now if you consider this ft correction factor, ft correction factor in mean temperature difference, what we have considered, delta T mean should be equal to ft into delta T Lm. Okay, so as ft value will not move beyond 1, so if you consider ft, it will reduce mean temperature difference. Okay, it will reduce delta T mean. Okay, but if delta T mean will be reduced, then what will happen? If you consider overall heat transfer coefficient fixed value, then also your area will be increase. Okay, so ft value you cannot uh, bring to very low value, otherwise area will increase many fold, which will give very high capital investment. Okay, therefore we put a bar over here that ft value should not be less than 0.75. Okay, so we consider ft value from 0.75 to 1. Okay, now if for a given combination, if your given combination of r and p, okay, R and P, if your FT correction factor will lie in this region, that is below 0.75, what you need to do to correct that? You need to consider, you need to increase the shell passes. Okay, if it is 1 2 shell and tube heat exchanger, in that case you should consider 2 4 shell and tube heat exchanger. Okay, so please consider that in mind, that ft value should not be less than 0.75. It has to bring to the above region, that is feasible region, which is shown over here. Okay, not in infeasible region. Infeasible region, when I am saying it, uh, uh, does not mean that uh, design is not possible over there. Design is possible with uh, with a very high heat transfer area, and further it when it is very low, it gives infeasibility in movement of the temperature. Okay, so that is also the case. So better is to consider ft value more than 0.75. Number of shell you need to increase. Okay, so that is about ft correction factor. If you have any query, you please discuss. Okay, so this is about ft correction factor, and the basic design parameters. We have discussed u, how to choose overall coefficient, and we have discussed delta T mean. Okay, so once you have these value, you already know q value, so you can find out heat transfer area. Okay, so that is about basic design parameter, and now we will see some of the factors which are used in designing. Okay, so here I am having one aspect is the fluid allocation. Okay, how to assign the fluid to shell side or tube side. Actually, whatever heat transfer course you have read so far, in that also you must have considered some of the problems related to shell and tube heat exchanger, either to calculate heat transfer area or heat transfer coefficient and all. But in all that cases, you were already given that which fluid is moving in tube side, which fluid is moving in shell side. Okay, but here when we are considering design, from the design means you are not given all parameters you need to collect. Okay, so how to count this factor, that which fluid should be allocated to which side, either shell side or to tube side. Okay, and to do that, there is basic rule is whatever what we can say, whatever uh, worst or bad you have to do. Okay, please listen it carefully. Whatever bad you need to do in shell and tube heat exchanger, okay, or whatever is the worst condition, that should be done with tubes, not with shell. Okay, so every factor which gives some something worse condition, that should be allocated to tube side, not in shell side, because tube cleaning of tube, changing of tube, and cost which is involved in tube, that is comparatively very less in comparison to shell. Okay, you can consider the shell dia as well as tube dia is very less, though number of tubes are there, but still tube diameter is so less that it can have very thin sheet. It means less material will be involved. Okay, however, if you consider the shell diameter is significantly high in comparison to tube, so more material will be involved in shell. Cleaning will be difficult in shell side, right? So in that case, this that this thing you need to keep in mind, whatever bad, whatever worse is there, that should be allocated to tube side. So please consider this, and based on that, uh, whatever points we are going to discuss, you please understand based on that factor only. Number one is the corrosion. Okay, corrosion again will damage the material. Okay, so obviously, if you are having more corrosive fluid, that should be allocated to tube side, not in the shell side. The reason could be, when you are considering the tube, okay, as I have told you, it includes less material. Okay, and to handle the corrosion, uh, because obviously when we are considering the corrosion or corrosive material, we don't want that our tube material or shell material will be damaged. Okay, so in that case, you need special alloys to make the what we can say, tube or shell. Okay, and that alloys are expensive in comparison to usual material of construction. And as I have told you, making of tube is cheaper in comparison to shell. So obviously you can make tube with expensive alloy in less cost in comparison to shell. So more corrosive fluid should be allocated to tube side, not shell side. Similarly, if you are considering fouling, okay, I hope you understand the difference between corrosion and fouling. Corrosion damages the material, okay, by what we can say, by some reactions and all. Okay, fouling basically, it is only the deposition. Okay, deposition of the material on the heat transfer surface. So again, more fouling fluid is there, you need to place that in tube side. Okay, not in shell side. Similarly, if I consider uh, fluid temperature, if the temperatures are high enough to require the use of special alloys, placing the high temperature fluid in tube will reduce the overall cost. So if temperature is there, high temperature is there, that should be allocated to tube side. Okay, and in that case there is another point, okay, another very interesting point. Like if you are considering temperature, high temperature, in that case that high temperature will give what we can say, expansion in the material. Okay, so in accommodation of expansion in tube side is easy in comparison to shell side. Okay, this point we will also discuss in detail while discussing the different type of shell and tube heat exchanger. Okay, based, this is a very important criteria to decide the type of shell and tube heat exchanger. I am not talking to type of exchanger, type of shell and tube heat exchanger. Okay, so this is about the fluid temperature. Another parameter I am having is the operating pressure. Operating pressure, if high pressure is there, that should be allocated to tube side. Again, the if high pressure, we consider more thickness, and that thickness will depend on temperature, depend on diameter also. So that diameter of tube is less, so less thick wall will be used for tube in comparison to shell. Therefore high pressure tubes will be cheaper in comparison to high pressure shell. So pressure in high pressure fluid should be should be allocated to tube side, not shell side. Okay, now viscosity. When we consider the viscosity will what we can say, reduce the heat transfer coefficient, because the movement of the fluid will be difficult in that case. So generally generally the heat transfer coefficient will be obtained by allocating more viscous material to shell side. Okay, provided the flow is turbulent. Okay, now if you consider the shell side structure, okay, if you observe the shell side structure, that is very zigzag type, because tubes are available in a definite pattern, either it is a square type of or rectangle type of. Okay, so tubes are arranged in such a way so that the movement or the flow between tubes will be very hazy in shell side. So if the fluid will be hazy, it is better for viscous fluid to have more turbulence. Okay, instead of we are providing that in tube side. Okay, so you need to consider viscous fluid to shell side if it is in the turbulent region. And when we consider the geometry of the shell side, critical Reynolds number for turbulent flow will be only 200. Okay, however if you consider straight pipe, straight tube, there you get the turbulence like around 4000 or so Reynolds number. Okay, Reynolds laminar will be up to 2100. Okay, so in that case if turbulence you can obtain, it means Reynolds number, if you have more than 200, allow the viscous fluid to move in shell side, not in tube side. Okay, if turbulent flow cannot be achieved in shell side, it is better to place tube fluid in tube, as tube side heat transfer coefficient can be predicted with more certainty. Okay, so in that case if viscosity is in turbulent flow is in turbulent region, more viscous fluid should be allocated to shell side. Otherwise every time you need to consider the tube side. Okay, so these are some of the factors. Based on that, fluid allocation will be done. Another parameter is stream flow rate. Allocating the fluid with lowest flow rate to shell side will normally give more economical design, and the reason is very simple, that if flow rate is less, okay, flow rate is less, and because of the geometry of the shell side, turbulent can be achieved easily, okay, in shell side in comparison to tube side. So less flow rate should be allocated to shell side. Again here the same point, more fluid flow rate should be allocated to tube side. Okay, now these are some of the parameters which we have discussed, and now we will see the criteria for fluid placement in order of priority. Okay, which parameter you should consider first to allocate the fluid. Okay, if I consider tube side, okay, corrosive fluid, if you know the tendency of the fluid, okay, corrosive fluid should be allocated to tube side. That we have already discussed, right? Here I am discussing the priority. Let's say if you are dealing with corrosive fluid, okay, allocate that to tube side first. Okay, even if that is what we can say, high temperature, high pressure, whatever, okay, but the priority should be given to corrosive fluid. Okay, next I am having the fouling fluids. So let's say if you are not aware of corrosive tendency of the fluid, if you aware that fouling tendency of the fluid is more, how you can consider that? Based on dirt factor table. From dirt factor you can already identify that which fluid is having more dirt factor. Okay, so that should be allocated to tube side. Okay, other fluid should be allocated to shell side, right? In that case you could have like if you are dealing with the fluid which is having higher fouling tendency, at the same time which is having what we can say, other fluid is having high pressure. I hope you are getting my point. One fluid is having higher fouling tendency, another fluid should be having higher pressure. Ideally, both should be allocated to tube side, but priority we need to give to fouling fluid. So, fouling fluid should be allocated to tube side, and high pressure fluid should be allocated to shell side. Okay, so in that way this priority table you need to consider. Similarly, if I'm having condensing vapor, if it is not corrosive, it should be allocated to shell side. High viscous fluid should be allocated to shell side. Low flow rate should be allocated to shell side. But in this priority range, okay, this table you will not find in the book, so please keep this in mind. Okay, this you need to remember that which type of fluid should be allocated where and in what order. Okay, so that you need to consider, okay, for allocation of the fluid. Okay, so that is about the fluid allocation to shell side and tube side. Now here I am having some of the limitations of shell and tube side velocity which you need to consider in design. Actually, why we are discussing so many things before starting the design? Because in the design it will be very easy for you to relate. Okay, therefore I'm not I'm considering all these parameters which are important in designing well before then the design of the shell and tube heat exchanger. So typical design velocity we need to consider for tubes. For liquid, if I'm having the liquid, tube side flow rate, sorry, tube side velocity should be 1 to 2 meter per second. Okay, that is the permissible limit. If you are dealing with process fluid means other than water. Okay, process fluid means other than water. So process fluid, if you are considering, velocity should be 1 to 2 meter per second. Okay, maximum 4 meter per second if required to reduce fouling. Okay, so if you are dealing with very high fouling tendency fluid, you can move up to 4 meter per second. Okay, and that per second. The reason could be usually water has more fouling tendency in comparison to process fluid. Therefore, here slightly more velocity we consider. Okay, so tube velocity 1 to 2 meter per second. What in case of fluid other than water. In case of water, it is 1.5 to 2.5 meter per second. Okay, now if the velocity of the tube side velocity will not fall in this range, then you need to change certain parameters to bring it to this range. Okay, once you bring it the velocity in this range, then you will proceed further. Otherwise your whole design uh, will not be acceptable. Okay, similarly for shell side, it is 0.3 to 1 meter per second. In case of vapor, if we need if we are dealing with vacuum, it is 50 to 70 meter. Atmospheric pressure 10 to 30 meter per second, and high pressure 5 to 10 meter per second. Okay, so in that way certain velocity ranges are there which you will use in design. Okay, next is the pressure drop. Okay, just a moment. Just in a couple of minutes I will start, please. Yes. So actually, when we consider this, another parameter is the pressure drop, which you need to bring to the uh, feasible range, and that condition is when I'm having the liquid. Okay, it depends on the viscosity. So pressure um, should be less than 35 kilonewton per meter square, and if it is viscosity is in this range, it should be less than, it should be in this range 50 to 70. Okay, so these are some of the design parameter you can see for gas and vapor as well. So these design parameter you need to consider in that for feasible design of shell and tube heat exchanger. Okay, so that is about the that basic design parameters and other factors. And now I will start with the shell and tube heat exchanger. Okay. uh, Actually many people have left from you, so should I continue?
Yes, ma'am, we can.
Okay, okay. So just let me share. So let me share my screen again with another topic. So is it visible that shell and tube exchanger construction details?
No, ma'am. Your screen is not shared. Okay, I think now it is.
Uh, it is not visible?
Now it is visible, ma'am.
Okay,
Previously it
okay.
was.
Uh, you are able to see this shell and tube exchanger construction details, right?
Yes, ma'am.
Right, right, right. So actually, yes. Okay, so as far as this shell and tube heat exchanger is concerned, first of all, we will discuss the construction details, and then we will proceed for design details. Okay, so construction details means what are the accessories in this shell and tube heat exchanger, and how we need to consider what are the guidelines available for these accessories to. So quickly I will see some of the basic points about the shell and tube heat exchanger. This is only for your knowledge purpose, okay? These are not construction details or something. This you should aware. Like when we consider shell and tube heat exchanger, why it is so important? Because if you consider chemical plants, okay, chemical plants, primarily oil refining, chemical and petrochemical plants and power companies, it has whatever heat exchangers are available, around 85% of heat exchangers are shell and tube type. Therefore this is so important, okay? And why 85%, that much number is for shell and tube heat exchanger? The reason is it can be designed for almost any duty with very wide range of temperatures and pressure. So temperature and pressure condition of wider range that can be we can accommodate in shell and tube heat exchanger, okay? Can be built in many material of constructions are these are available, uh, what we can say, many materials are available for construction of this, okay? Many suppliers, okay? You can buy the shell and tube heat exchangers from like we have we have number of suppliers very near, local suppliers also you can get that. So that is very easy to get this shell and tube heat exchanger. Design methods and mechanical codes have been established from many years of experience. So here we have the design methods which are established, and mechanical codes are used for mechanical design of shell and tube heat exchanger, okay? Mechanical design, that we have already seen the pressure, like how to deal with mechanics and all, okay? So for that we have a particular code, I think it is IS 4305, okay? So as we have considered IS 2825 for this pressure vessel designing, okay? So when we consider the variation in temperature, in shell you can have up to 300 bar, okay, which is very high. And tube side, when you are considering, it is 1400 bar, okay? More you can accommodate in tube side for the same reason which we have discussed before, like it has less thickness because of less diameter for the high pressure, okay? Temperature range maximum 600 or 650, minimum minus 100. So that is the very wide range. Fluids, when we are considering, subject to material, you can use any type of fluid, whether it is corrosive, whether it is fouling, whether it is viscous, okay? All that you can accommodate over here. Available in wide range of material, okay? So that because uh, material of construction are available in wider range, so that therefore you can accommodate the different types of fluids also in this, okay? Size per unit, that it varies from 100 to 10,000 feet, or 10 to 1,000 feet, 1,000 meter square, okay? In that you can say yesterday we have discussed for double pipe heat exchanger, there we have observed that 50 meter square, beyond that double pipe is not feasible, is sorry, double pipe is not what we can say economical, okay? But here if you consider the range, we have started from 10 meter to 1000 meter, but shell and tube heat exchanger we usually consider beyond 50 meter square. So why this is 10, okay? 10 to 40, 10 to 50, what will happen? 10 to 50 also you can design shell and tube heat exchanger, there is no problem, but that fabrication cost will be very high in comparison to double pipe. Therefore it, though it can um, fabricate, it can design from 10 to 1000 meter square heat transfer area, but we will consider up to we will consider this beyond 50 meter square. Okay, I hope you understand. Okay, so these are some of the points, and now we will consider the shell and tube heat exchanger and its classification. We have discussed classification of exchangers, but this is specifically for shell and tube heat exchanger. And uh, when you go for the design of shell and tube heat exchanger, you need to choose a suitable heat exchanger of shell and tube type. Okay, therefore you should understand what are the different shell and tube heat exchanger, and in which case which one is more suitable. Okay, so first category in that is fixed tube sheet. Then we have U-tube shell and tube heat exchanger. We have internal floating head shell and tube heat exchanger, and external floating head shell and tube heat exchanger. And beyond that, we have other heat exchanger also, which fall in the category of external floating head and internal floating head. Okay, mainly external floating head. Okay, but the major classification when we consider here, we have these four types. Okay, so we will start with fixed tube sheet. Okay, so this is the schematic of fixed tube sheet, and we have different numbers over here. You can see these part number, and that you can see that you can read from this on your own. But the main emphasis which I would like to speak on over here is, this is fixed tube sheet. Fixed tube sheet means tube sheet is fixed with the shell. Okay, the purpose of tube sheet is to differentiate the liquid of shell side and tube side, that we have discussed yesterday, right? Second is to hold the tubes. Okay, now if you consider tube sheet, this is tube sheet. Okay, if you consider 6 number, okay, 6 number over here is fixed tube sheet, tube plate. Also we call this as tube plate. Now this is tube sheet. Another tube sheet is available over here. Okay, and if you consider this particular part and this particular part, this is called as cover or channel. Okay, if you see, this is 7 number, this is channel, and that we also call this as cover. Sometimes channel cover is also defined. That 8 number is not available over here, that will be in subsequent heat exchanger, subsequent type of heat exchanger. Okay, we'll discuss that further. Okay, now if you consider this tube sheet and this tube sheet, these tube sheets are directly welded with shell. Okay, this is the shell, right? This is the shell and this is the tube sheet, and this tube sheet is welded with this shell here as well and here as well. Okay, the point is, uh, this as this tube sheet is welded with the shell, you cannot change, you cannot do anything for replacement of this. What we can say, if some problem will be there, then you need to discard this. Okay, what we can say, deassembling or reassembling is not possible over here because of this fixed, because of this welding, permanent joint is there, right? Okay, now if I consider this fixed tube sheet, okay, and this cover, if you are considering, or this channel if you are considering, this can be attached with this bolt. Okay, that you can see this line. Okay, this line as well as this line, right? So that cover will be attached with tube sheet, but tube sheet is permanently welded with the shell. I'm repeating again and again. Okay, now what will happen over here, like if you are dealing with the high temperature, okay, if you are dealing with high temperature, we have discussed before that high temperature fluid should be allocated to tube side. So if this is the case, that tubes it will flow in tube side, and if temperature will be higher, you can expect certain type of expansion in the material. Okay, expansion will be there, but here because this it is permanently fixed with the shell, that expansion is not possible to accommodate over here. If we will consider high temperature over here, tube will bend but it will not expand. Okay, because of that temperature, more temperature, bending may occur but not the expansion. I hope you are getting my point. So when I'm considering with tube sheet, fixed tube sheet, there is no provision for differential expansion or contraction. Okay, therefore it is limited up to the temperature of 100 degrees Celsius. Beyond that you cannot use fixed tube sheet. So if you have usually you aware of all temperature differences, sorry, all terminal temperature of cold fluid as well as hot fluid. So if your temperature, maximum temperature among this, if it is available, if it is less than or equal to 90 degree, then only you will choose this fixed tube sheet. Okay, okay, because it is not accommodating differential expansion or contraction. This type of heat exchanger are very cheap, or we can say of less cost in comparison to others which we are going to discuss. Okay, so you will choose this heat exchanger when temperature of maximum temperature given in the problem is less than or equal to 90 degree, not beyond that, right? So this is fixed tube sheet and we have this limitation. Okay, we need to, we cannot include thermal expansion or contraction. So to avoid this limitation we have another heat exchanger which is U tube heat exchanger. Okay, so when I'm considering this U tube heat exchanger, uh, uh, this is a U tube type, okay, or we can say the hairpin type. So all tubes are of U shape, okay, and in that case we have only one tube sheet. Okay, if you see the fixed tube sheet, there I am having tube sheet here as well as here, both way. Okay, however in this case we have only one tube sheet. Okay, in that, in this side there is no tube sheet. Okay, because there is no what we can say, tubes are not what we can say ended over here, they return back, and the second part will be welded over here also, over here only. Okay, so only one tube sheet, and if you consider the shell will be attached with this tube sheet and with this covered through the what we can say bolt. Okay, so when you deassemble it, you can remove this cover, you can take this bundle out, you can keep this shell apart. Okay, but that is not possible in fixed tube sheet because their welding is done. Okay, so this is only one tube sheet, and here I am having this U tube. Okay, so as whatever the limitation of fixed tube sheet, that it cannot accommodate thermal expansion or contraction, this can accommodate. How? Because here tube sheet is fixed. Okay, where tube sheet is there where tubes are fixed, but here tubes are not fixed. Okay, tubes are not attached with the tube sheet. So if you consider this particular space can be used for thermal expansion and contraction of this tube sheet. Okay, so the point is you can accommodate high temperature liquid beyond 90 degree or 100 degree in U tube. Okay, because possibility of expansion and contraction is there, so that you can do. But what will happen when you allocate the fluid to tube side? Okay, and if you see this bending, okay, this is very difficult to handle this bending. Okay, if you are if you deal with the fouling tendency fluid or corrosive fluid, it is very difficult to clean this part. I hope you understand. This bend part is very difficult to clean. Therefore, though you can accommodate high temperature, but you cannot accommodate fouling fluids or corrosive fluid in this. Okay, so limitation of U-tube is these can be used to relatively clean fluids. Okay, so if you, how when you will choose this U-tube, like your U-tube has very less dirt coefficient. Okay, sorry, dirt factor. How you can identify that? Based on the dirt factor table, if the dirt factor given for the fluid is less than the range given in that dirt factor table, you can allocate that to tube side if it is at high temperature. Okay, however, if it is it does not have high temperature and fouling fluid is there, you can use in fixed tube sheet, there is no issue. Okay, so the limitation of U-tube is it is used for cleaner fluids. Okay, so that is the thing. So here we have solved the problem of temperature, thermal expansion and contraction, but again we have the limitation for cleaner fluid, so we need to go for another heat exchanger which can accommodate both the things. Okay, like high temperature and fouling tendency as well. So that heat exchanger we have is the internal floating head heat exchanger. Okay, internal floating head heat exchanger, if you consider, here I am having the tube sheet, this is the shell and this is the cover. All these three things are different. Okay, that can deassemble very easily. Okay, and if you consider this tube sheet, okay, another part of the tube sheet is this. Okay, another part of the tube sheet is this, and in that case, um, tube sheets are inserted in this tube sheet as well as in this tube sheet. Okay, so this we call as floating head cover. If you see number 3, this is floating head. Floating head means this this is fixed. Okay, but this complete section along with this tube sheet, this tube as well as this cover, it can float in this region, it can move backward and forward in this region. It means high temperature can be accommodated over here. Okay, and as bending is not there, tubes are straight, which is very easy to clean, you can consider this tube this type of heat exchanger to handle fouling tendency fluids as well. Okay, so whatever are the limitation of what we can say, a fixed tube sheet and U-tube heat exchanger, that can both can handle over here. Okay, so this is the thing. Now this is very a win-win situation, like everything we can accommodate over here. Okay, so if you see, this is more versatile than fixed head and U-tube heat exchanger, suitable for high temperature differentials because it can accommodate expansion and contraction, easier to clean and can be used for fouling fluids because tubes are straight. You can simply deassemble the bundle from here. You can take it out, you can take the bundle out, and then you can deassemble this part also. So tube will be straight, you can clean them very easily. Okay, but what is the problem? The problem is because this tube sheet, okay, if you see the diameter of this tube sheet as well as this tube sheet, the diameter is different. Okay, this tube sheet is having less dia in comparison to this. Okay, however, this tube sheet will be available inside the cover which is having same diameter as the shell. Okay, please try and understand what I'm trying to emphasize on. This is the, because this section floating, floating you will consider. Okay, it means floating if you are considering, so whole section should be inside this cover. Okay, inside this cover, this complete assembly should be there. And if I'm considering this cover, uh, the particular diameter will be this cover has a particular diameter which is more than the diameter of this tube sheet, and the diameter of shell will be of the same order of this cover. Okay, now the point is this much you are accommodating over here, and if I consider the same diameter of the shell, there is no tube available over in this region. Okay, there is no tube available in this region. So the limitation of this type of internal floating head heat exchanger is the clearance between outermost tube in bundle and shell is made larger, made greater. It means this gap and similar gap will be available over here, which you cannot see because of this only upper section is shown over here, but you can see this section or this region is quite high in comparison to other. Okay, please see this region, and if you see the U-tube, this region is comparatively lesser. Okay, similarly in internal floating head, this region would be comparatively lesser. Okay, but that is more in shell and tube so in internal floating head heat exchanger, because this is the integral part of the exchanger. Therefore it is called internal floating head because it is moving inside the exchanger only. Okay, so to accommodate that, we need to have more clearance between this. Now if more clearance will be there, there are more chances to have a dead zone in a heat exchanger. At the same time, you need to consider shell diameter of high value in comparison to other heat exchanger. Therefore this type of heat exchangers, though it is very versatile, but it is very costly also, right? So in that case, what we need to do, we need to consider floating head, but not with this clearance. Okay, so in that case we have another heat exchanger which we call as external floating head. Okay, internal floating head, if you see, this is another image I have shown you for clarity. This is second tube sheet which moves in this region. Okay, in this cover, which is having same dia as the shell. Okay, if you see here, we have more what we can say clearance, in which liquid will stay and which will not participate in heat transfer. Okay, and which we consider as dead zone. Unnecessary, we are providing larger diameter shell, and so it is very costly. But the if somehow I can keep this section out of this heat exchanger, so flotation will occur at outer part, but here we can have lesser diameter shell. As you can see over here, if you consider this tube sheet resembling to this tube sheet. Okay, so this tube sheet I am having, and this is the shell. Okay, so this tube sheet is attached with this cover, where this tube sheet can move forward and backward. Over this, it slides over here. Okay, so this we consider as external floating head, where this is a specific type of assembly which is over which this tube sheet floats, or we can say slides backward and forward direction. Okay, so if you are considering this, this is a part of shell, right? And this is what we can say tube sheet cover, and here I'm having another assembly. Okay, this L-shaped type. So this can this shell can be attached with this L-shape assembly, and in between we keep the gasket for to have a leak proof what we can say, to have a tight connection. Okay, between these two, and whatever that metal parts irregularities are there, that can be filled with this gasket. Okay, but the problem is, though it can accommodate high temperature, it can accommodate uh, what we can say fouling tendency. With less diameter shell, everything is positive over here, but the point is when this slides, okay, when this tube sheet slides over here, if it is if contraction is there, it is no problem, it will move in this direction. However, if expansion is there, it will move in this direction, and if expansion would be quite high, this part can come here, and there are chances for liquid to pass to leak from this connection. Okay, and in that case we can consider that if your fluid is having toxic nature, if in flammable fluids if you are using in shell side, in that case external floating head should not be used. Okay, so if you need to accommodate more toxic fluid, more in flammable fluid, allocate that to tube side, because there is no possibility of leakage. Okay, therefore floating head joint is located outside the shell, as you can see over here, and the shell sealed with the sliding gland joint. This is sliding gland joint over which this section slides. Okay, because of the danger of leaks through the gland, the shell side pressure in this type is usually limited to 20 bar, and flammable or toxic material should not be used in shell side. However, that can you can use in tube side. Okay, so in this way, if you are dealing with toxic fluid, okay, uh, if you are dealing with toxic fluid, that can be accommodated in internal floating head anyway, either in shell side or in tube side. Okay, so this is most versatile but expensive as well. Okay, so what is the overall conclusion over here? If the maximum temperature you are uh, dealing with in a heat exchanger uh, less than or equal to 90 degree, you can choose a fixed tube sheet. Okay, if you are dealing with more than 90 degree but fluid is clean in nature, you can choose U-tube type. Okay, if your fluid is toxic in nature, temperature is higher, fouling tendency is there, you can choose internal floating head. Okay, if your fluid is having like high temperature, external high temperature, fouling tendency and toxicity, flammable fluid is there, you can use external floating head also, but that in that case fluid should be allocated to tube side. Okay, and I have already told you the bad whatever bad you are doing, please do that with the tubes, not with the shell. Okay, so in this way you can choose different type of internal floating, sorry, different type of shell and tube heat exchangers. Okay, so that is about the classification of shell and tube heat exchanger. And now we will proceed with the uh, construction details. Construction details, when we consider the first accessory we are considering over here is tubes. Okay, so how to choose tube diameter as well as length. Okay, because once you choose the tube diameter as well as length, you you can calculate the heat transfer area of one tube, and you already calculate overall you calculate total heat transfer area based on assumed overall heat transfer coefficient. So from that you can find out number of tubes. So here we need to consider two different parameter, tube diameter as well as tube length. Just 1 minute, I'll start. So tube diameter, when we are considering, there is a specific range. Okay, the range is a tube diameter used in shell and tube heat exchanger vary from 16 mm to 50 mm. Okay, 16 mm to 50 mm, but uh, the more preferred range is 16 mm to 25 mm. Okay, which gives more compact, cheaper heat exchanger. Actually, what will happen when you are dealing with less diameter tube, okay, you what we can say, you if tube diameter will be less, okay, tube sheet diameter will be less, and so shell diameter will also be less, okay. So we can say usually that heat exchanger should be thin but should be large in length, okay. So in that case, preferred range is 16 to 25, okay. However, when we consider the whole range 16 mm to 50 mm or 16 mm to 25 preferred range, you cannot choose any value between this 16 to 25. Let's say if I am having 16 mm, you can choose 18 mm. No, you cannot choose. You can choose only those value which are available in market, and that I'll show you what these values are. So between the values which are available in market, between them you need to choose the diameter which fall in this range 16 to 25 mm. I hope you are getting my point, okay. So larger tubes are easier to clean by mechanical methods and would be selected for heavily fouling fluids. So if you are dealing with fouling tendency fluid, more fouling tendency fluid, you can reach beyond 25 also, because it is easier to clean. Okay. Now this is the standard table which I will provide you. This table is in annexure of R.W. Surth book. This is not available in volume 6. So I will provide this table to you, no problem. Okay. So this is the standard table of tube. If you see here, I am having tube OD. Okay, tube outer diameter. And here we have the value 1.5, 1 by 2, 5 by 8, 3.4. So between 16 to 25, you can choose only these diameters. Okay. Now if you consider this, what we can say, 5 by 8. Okay, 5 by 8, if you are considering 20. So it will be around 15 mm, 15 mm or so. Okay, which is a little bit lesser than the 16 mm, which is the starting value. So you can have this. Just a moment. Yes. So this would be lesser than 16 mm, which is the recommended value for tube OD. So 3 by 4, if you are considering, 3 by 4 will give you OD in mm as 19.05, which is between 16 to 25 mm. I hope you are getting my point. So you can choose this OD or beyond that up to 25 mm. Okay, this table is not this much only. It is quite long table. Only one section of that I have pasted over here, but I'll provide the complete complete table to you. Okay, so you can choose this 3 by 4. Second column I'm having is BWG value. This BWG value is basically Birmingham wire gauge. Okay, this is Birmingham wire gauge. This is given a particular standard number. Okay, you must have read in maybe in your fluid mechanics course about the pipe, that is there is a particular number which we call as schedule number. Okay, schedule number tells about the thickness of the pipe. Okay, similarly Birmingham wire gauge value tells about the thickness of the tube. Okay, so depending upon different BWG value, we have tube ID, standard tube IDs. Okay, and so the internal area and other parameters are given. So if you are considering this 3 by 4 as tube OD, you can choose any BWG value, and correspondingly you can choose tube ID. It is recommended from this whole range 10 to 20, it is recommended to choose the value in between. Okay, because uh, this heat exchanger design is already an iterative method. So if you choose a middle value or average, I should not say average, but middle value from here. um, it will give more feasible results, and it will give less iterations. So 3 by 4 you can choose, and let's say 14 bwg value or 15 bwg value you can choose, and you can have this tube id from here. You cannot consider any other value, please keep in mind. Okay, whatever is available in this tube, from there only you can consider. However, if you choose this 3 by 4, you can choose 10, you can choose 20, no problem, but it is better to start from the middle. So accordingly you can have tube id. Okay, so once you fix tube od and id, you can fix the tube sheet thickness. Okay, so in that way you can choose the tube diameter. Next we have the tube length. Okay, so preferred length which are used for the tube, which are available in the market. Okay, these are 6, 8, 12, 16, 20 and 24. These are the lengths which are available in market. You cannot consider 7 feet or 10 feet like that. Okay, if 6 feet will not work for you, you can choose 8 feet directly, and then 12 feet, not in between. Okay, so these are the standards. But how to choose how to choose a proper length? Okay, proper diameter you can choose between this range, but proper length should be chosen uh, based on ratio of tube length to shell dia. Okay, like if you are having the this diameter, let's say you have chosen the 8 feet as a length, and 3 by 5 as a dia, outer dia. Okay, so based on that you can calculate area of one tube. Okay, you already know total heat transfer area, divide by this area of one tube, you can find number of trays, sorry, number of tubes. Once you have the number of tubes, you can calculate shell diameter. We will discuss that further also. So once I am having this shell dia, you will take the ratio of tube length 8 feet, divide by that shell dia, and it should fall in this range 5 to 10. Okay, if it is not falling in this range, you need to choose any other length. Okay, let's say if it is coming as ratio is coming as 12. Okay, it means that length whatever you have chosen, it is quite high. So instead of 8 you can go for 6. Okay, like this you can move, but beyond below 6 you cannot move. Then you need to think about any other parameter to change. Okay, therefore we always say that whatever design methods are available, all these design methods are based on intuitions. If values, let's say if you are considering initially 12, okay, and this is falling well beyond then 10. Okay, let's say 12 or 13 is there, you will choose 8 feet, you can choose 6 feet, there is no issue, but it is better to choose a subsequent value. Okay, therefore if anyone is choosing 8 meter or others are choosing 6 meter, there is no problem. Okay, the thing is it should be in this among these values. So in this way you can choose shell in, you can choose diameter of tube as well as length of the tube. And uh, yes, so this is all from my side for today, and I will I will continue in next class. Okay, so if you have any observation or any confusion, any question, you please ask. So that's all from my side for today. Thank you. Okay.
Thank you, ma'am.
Thank you, beta. Thank you. ठीक है. So I think we will continue in next class this designing part. If you have any observation, you can email me also, no problem. So thank you all for your patience. Thank you.
Thank you, ma'am.
Thank you.